Well, welcome to the Dask talk. We're running a little bit late. My name is Jim Crist. I work for Continuum Analytics. So we're going, well, first actually, how many of you have heard of Dask or heard something about Dask? Okay. Oh, there's a lot of people. Cool. Cool. Well, that's excellent. So we'll start with a motivating example, just to get things going. We'll start with this. This is the link to the materials if you want to look at them later. There are some examples I'm going to run through that are not in full, but they're up online on notebooks, so you can pull them down from GitHub later. OK, so motivating example. I have some ocean temperature data. It's a daily mean ocean temperature data taken in a grid 720 by 1440 array every single day. And this goes back for years. This is all provided from that URL right there. So using Python, it's really, really easy to analyze a single year's worth. You can open up with netcdf4, which is just the data format library, and then use matplotlib and NumPy to run a little bit of analysis and make a plot. And that all happens pretty quickly on your computer. It's just a few lines of code, very simple to work with. So here we're averaging the 1 year's worth of data to get the mean ocean temperature data for that entire year. But what happens if I have more? So this is 36 years worth of data, each one stored in a yearly file. It's about 15 gigabytes on disk, but that's compressed. And so if you were to decompress it, you actually end up with about 51 gigabytes uncompressed, and that is a lot bigger than the RAM on my laptop. I can't easily work on that on my laptop. So are we stuck? Can't load it into NumPy. Do I have to move to Spark, some distributed something or other? Well, not quite. So we can use blocked algorithms, which is what I'm going to be talking about mostly today. So what is a blocked algorithm? Well, here is an example. So this is the blocked mean. So let's say you have a data set stored in an HDF5 file. It's a trillion element array. It's on disk, whatever. And you want to actually take the mean of that. Well, you don't have to read all trillion elements in at once. You can actually do it in an iterative approach. So you can split it up into 1 million sized chunks. And then each chunk, you can sum it all together, so you get the sum of each chunk, and then you can count how many elements are in each chunk, which in this case is always going to be 1 million, but you can think of other cases where it wouldn't be. And then at the very, very end, so each chunk then you store. So we'll store all the sums of each block, and we'll store all the counts of each block. And at the very end, we're going to sum all the sums together, we're going to sum all the counts together, and we'll divide. And so this is kind of a map of some operation across all the chunks, and then some kind of reduction at the end. And so if you look at this loop, this iterative, 1 chunk, 2 chunk, 3 chunk, none of the operations depend on the previous thing in the loop. So Python would run this all in series. This would all go through, chunk 1, chunk 2, chunk 3, but they don't need to. You could split this up into parallel. And so that is what that would look like. So you have your original array, you kind of split it up, you do some operation all across all of it, and then you reduce it back together. And so using this kind of approach, this blocked algorithm kind of approach, you don't have to load the array into memory at once, so you don't have to use, have that much memory on your computer, that much RAM. And we can actually expose some kind of parallelism. So that's what blocked algorithms get you. They get you parallelism. You can do more than one thing at once. Computers these days have more than one core. It'd be nice if we could use all of them. And they can lower your RAM usage. You can work on data sets that are bigger than the RAM on your computer. That's what we'd call out of core. So data that fits on disk but doesn't quite fit into memory. So blocked algorithms allow for parallelism and lower RAM usage. The trick is figuring out how to break computations into a blocked fashion. So for something like this, it was pretty simple. We're summing each chunk and we're counting each chunk. And then we're doing a final reduction, just a simple MapReduce pattern. But other things can become more complicated. And so this is where Dask comes in. So Dask is a parallel computing framework that leverages the excellent existing Python ecosystem. So we have NumPy, we have Pandas. All of those work great. We don't want to rewrite those. We just want to kind of use them, but somehow make them parallel. It uses blocked algorithms and task scheduling, which we'll talk about a little bit more later. And it's written in pure Python, so it's really, really easy to install. It's const installable, pip installable, nothing to compile on our end. If you have NumPy, everything should just work fine. So at the base of Dask, in the red right here, we have what we'd call the Dask core. So it's all built on a simple graph specification, which we'll talk about in a few minutes, that just encodes how you describe your parallelism. And then on top of that, we have built some schedulers to actually execute these graphs in a parallel fashion. So we have ones that do it in threading. We have ones that do it in different processes. One is coming about that will do it across multiple computers. But it all comes from the same specification. And then on top of that, in the existing Python ecosystem, we built a few collections. So we have Dask array, which uses NumPy internally, and it kind of exposes an ND array-like object. But you can do parallel algorithms on that. Dask bag is kind of like Python list, except we don't enforce ordering, so there's no order to it. And Dask dataframe is kind of like a Pandas data frame. So Dask array, as I said, it's an out-of-core parallel n-dimensional array library. We support a lot of the NumPy interface. So we support arithmetic. You can do addition, multiplication, those kind of operations on arrays. We support common reductions, mean, max. We actually have a generalized moment calculation if people want to do some stats. Slicings. So normal slicing you do. We also support fancy indexing. Both of these can be done in a parallel fashion. And we support some linear algebra. So tensor dot, normal matrix multiplication, QR, SVD. We recently got SVD compressed, which is kind of a fun little randomized algorithm. So here's the fun part of the talk. I'm going to do a little demo here. Okay. So I'm importing the array library. Is that big enough? Can people read that? Good? Good enough? A little bigger? A little bigger? Okay. Actually, I think I can get this to go away too. Yes. Excellent. So Dask array imported as DA, it's a namespace. If I was to do tab completion on that, it looks a lot like things you'd normally see in NumPy. So we have some ufuncs like sign, but the main one that we're going to be using is from array to create an array. So to do that, I'm going to create a NumPy array of size 1,000 by 1,000. So just a square array, just for an example. Then creating a Dask array, da.from array. This takes in anything that supports NumPy style indexing. So this can be a NumPy array, but this can also be something like an HDF5 file. Things that you can actually pull some chunk out. It has to have a shape and it has to support slicing. So there's a lot of data stores, OnDisk data stores that support the same syntax, and so you can load those into arrays from that form. So we're going to pull that in from X, and the other thing we need is a chunks parameter. And so what this is going to do is this is going to say how we're going to block up our array. So we're going to store it in multiple chunks, which we can actually do parallel operations on. And so we're going to store it in 500 by 500 chunks. So it's going to be 4 chunks making our whole array. And so that's made a Dask array.
Does that value have to be fixed?
It has to be made at creation time. So you can do whatever you want for it. It doesn't have to even be even numbers, but it has to be done on creation. So tab on that. You can see the kinds of operations we support. So let's start creating things. Actually, we'll first visualize what's going on. So what you're seeing right here is the graph showing how the calculation is going to be done. Spit that out. OK, so what we have right here, this is showing how the array is going to be computed in memory. So we have our original array, the NumPy array, and then all it's doing is pulling out each chunk. And that's all the operations we've encoded right now. So let's take a sum of the whole thing. Note that that doesn't run. We haven't actually done any computation right now. We are building up a graph of the operations we're going to do. And you can actually visualize what that graph looks like at each step just by tagging on the visualize method. So here, we pulled out each chunk, and we're going to sum each chunk, and then we're going to take a sum at the end. And so we can keep chaining these together. Let's do mean across an axis, and then sum the whole thing together. So you can keep chaining these all together. We'll do matrix multiplication across its transpose, and then do the same thing. So you're getting more and more complicated. And so at some point, these are getting more complicated than you want to write by hand. But we've already encoded these blocked algorithms into Dask, so you don't have to build the graphs yourself. And then at the end, if you actually want to run this, you just call compute on it. And you get your answer out. And so this happened. Thread crawled through that graph in parallel and actually computed the result. Let's go back. Cool. So here we have a visualization of how one of the task schedulers running through a graph. So this is a very parallel. It's an embarrassing parallel operation. And so the scheduler is going to crawl through. And it's dynamically scheduled. So this is all happening at runtime. And the heuristic we use is we try to reduce the amount of intermediates that are held in memory. So we don't want to flood your memory. We want to make sure that we're pushing things all the way through so we can dump them and not use more RAM than we need. So in cases like this, it works out very well. We're going all the way through from start to finish for each one. And then all those intermediates in blue can be dumped. And so we don't actually have to keep them. Sometimes this breaks down, though. So in this case, at some point here, we're going to get the entire middle row all in red before it goes on. That is not a good use of the heuristic. Actually, this is old, so the Dask doesn't do this anymore, but it still fails for some cases. And so this actually isn't bad, though. We contain mechanisms to spill to disk, so we won't actually crash your computer when this is happening. So we try to minimize intermediates, try to reduce the amount of RAM that you're using, but in bad cases, things can still work. Quick question?
Yeah, do you able to set the limit of RAM being used?
We can set the limit of RAM being used for caching, but not for. Actually, no, we can. Using the chest project. And I can talk to you more about that later if anyone's interested. So as I said before, this is crawling through with threads. So some of you might have heard something about the GIL, the global interpreter lock. How many of you have heard that phrase before? Quick raise. Okay, everyone has heard about the GIL pretty much here. For those that haven't, the global interpreter lock means that a Python interpreter can only execute one Python instruction at a time. So running Python code in threads actually isn't really running it in threads. But in luck for PyData, it is. Oh, so this is, I like this GIF. This is most Python programs. It's heavily using one CPU and none of the others. So anyway, for PyData, this actually doesn't matter. We're running a lot of numeric C code or Fortran code, and so that all can release the interpreter lock and actually run in parallel. So this is using Dask to do what can actually be done in memory with NumPy, a threaded operation for matrix multiplication, and then doing a sum along a single axis. And so what you see below that, this is a profile plot. Dask actually generates these. We have nice diagnostics tools. And so we have 4 workers, so each of those is a thread. And you can see the nice Gantt-style chart going through where they're all being fully used. And the plot on below is showing my CPU and my memory. And almost immediately, we go up to using 400% CPU. So I'm actually using all 4 cores in a single Python process using just threads. And that's kind of nice. So in cases like this, for arrays, this is actually faster than using NumPy. But we've just done the special stuff using Python. This is all written in pure Python to make it work. So moving on. So that original example I had, doing the ocean data, we can actually do that computation on all 51 gigabytes of data using Dask. It's a few more lines of code. We're going to create, we're going to open up all the data sets using netcdf4. That just points to the file. No data is loaded at that time. And then we're going to concatenate them all together using Dask. So we're going to create a bunch of Dask arrays. We'll call da.concatenate on them to concatenate them all together into a single Dask array. We'll take the mean across the whole thing. At this point, we can treat it as a single big array. And then at the final bit, we'll pass it to matplotlib. So 2 things about this. 1, no computation has been done until that final plot command. 2, we didn't actually call compute on our Dask array ourselves. So the Dask exposes the array interface, which is something that NumPy has. And so functions that expect NumPy arrays and call numpy.asArray on their inputs if they're not, which is a lot of things in the PyData ecosystem, will automatically call compute. So for many array-based things, dropping in Dask works automatically, which is kind of nice. So here's the plot. This is all of the data from 1981 to 2015. It's about 51 gigabytes. This was all processed on my laptop, which does not have nearly that much RAM. Yeah, just using Dask. So moving on. I just put this in because I like this graph. This is the graph from SVD. It's mildly complicated. If this isn't fast enough, this is done in parallel and out, of course. You can do it on data that's bigger than your RAM. If that's not fast enough, we have the randomized one, which was also put in. And so this is not 100% accurate, but it is it's an approximate algorithm. That's what I'm trying to look for there. Okay, so now moving on. Dask data frame. So we had a Dask array, which copies the NumPy ND array interface. Dask data frame looks a lot like a Pandas data frame. Again, we do a lot of the operations that Pandas supports. So we can do element operations, so we can add series together. We can do selections, aggregations, group bys, resampling, expanding window computations. So a lot of things that you might want to do for working with time series analytics are exposed. We have out-of-core joins too, which is kind of fun. And you can create Dask data frames from many different sources. So a directory of CSVs is a pretty common use. You just glob, so the star.csv or whatever your file pattern is, you can create a whole data frame from just those, and it'll encode the loading operation, and then you can do computations based on that. Any Pandas object, well, not any series or data frame from Pandas works. Castra is an experimental data store. That's just in there for completeness. So here's another example. Out-of-core data frames. I have yearly CSVs of all American flights. This is containing information on the times, airlines, locations. It's about 121 million rows, 11 gigabytes of data on disk. You can get it from that URL there. So I was able to, again, analyze all of this on my laptop. Or actually do a live demo on this one, too.
Unlike the weather data, this one is the number of rows in each file is different?
Yes. So I have just CSV of how many rows. So that's a difference between arrays and data frames. Each chunk of a data frame doesn't have to have the same size. Well, each chunk of an array has to have the same size, if that makes sense. So I can load. I've already converted this into Castra just for speed reasons. You wouldn't have to do any conversion. This could be done directly from CSVs, but for a live demo, this is a little bit easier. So we'll import. So importing Dask data frame as DD. We'll create the data frame. So just loading it from Castra. And this already looks like a Pandas data frame. So some of these, tab completion, are column names. Some of these are methods. We'll look at the, I'll clear so that goes to the top. Look at the departure delay. So this is the delay of departure. We can take the max of it. So let's see. So this is the max of the max delay for each column. This is not computed yet, but we can compute on it to actually get the result. I'm going to let one run while I talk. So we'll take the departure delay. We'll group by the origin, so where it took off from. We'll take the mean of that, and then we'll figure out the 10 largest. So this is taking trying to figure out the maximum, the top 10 mean departure delays by airport over the entire time series, so all of the flights. And this is going to take about 40 seconds to run, if I remember correctly. But it's using a lot more data than I can actually hold in my memory. But we're able to do this out of core using Dask. So while this is running,
How large is the data set?
it's about 12 gigabytes on disk. So actually, that can fit on my laptop. But and we'll see in a second here, we didn't load nearly that much data at a time. Quick question? Is there something about disk I/O that I'm using? Yeah. That's hard to do in a cross-platform way. So for example, that's not supported on Mac, as far as I can tell, using PSUtil. Anyway, so this has gotten the results. I can take questions at the end, I'm sorry. This has got the results up here. This is not the best example of data science. If you actually look up these airport codes, most of these are extremely tiny airports in Alaska, and they have about 1 or 2 flights, and they were all delayed. So some kind of a normalization would be needed. But that shows it looks a lot like Pandas code, except it runs out of core, and in some cases recently parallel. Pandas is more and more releasing the interpreter lock. So back to the presentation. This is the profile plot from that exact same computation. So you can see the blue line there, the dark blue line, is CPU use. And so for parts of it, we're getting more than 100%, but for the most part, we're slightly above 100. So that's showing that most Pandas isn't nearly as parallelizable as the array stuff. And that's partly because of the interpreter lock, and that's partly because of the algorithms we're using. So moving on. The other collection I talked about is Dask Bag. We'll quickly, I'm running a little low on time, we'll quickly run through this. It's an out-of-core unordered list. So think of things that don't really fit the array abstraction, don't really fit the data frame abstraction, just some kind of collection of objects. So maybe a collection of JSON blobs or log files, general string processing. There's an example up on our Blaze blog. So about Reddit comments, the address is down in the bottom corner there. This is pulled out of that. So this is using Dask bag to generate a word cloud for all of the comments from our machine learning, so the machine learning subreddit. So we're pulling out the subreddit and body fields of all the JSON blobs. We're filtering for just the subreddits that are in the comments that are in machine learning. We're figuring out, we're plucking out the body field from each of those tuples. We're mapping a function to change the body into a list of words. We're concatenating those lists together, and then we're doing a frequency count and taking the top 10. And so this looks a little bit like the Spark API. It's a lot like most functional processing things. It's actually using a lot of the library tools by Matthew Rockin underneath. And if you actually plot that, this was kind of a happy thing that came out. The top 2 words in our machine learning are more in data. So this is using Andreas's word cloud library. So we've talked about the collections on the left here. We have Dask array, Dask bag, and Dask data frame, an imperative, which I'll talk about in a second here. And each of those creates a graph, which expresses some kind of computation. We've encoded a lot of parallel algorithms for common things that you might want to do. The graphs are then passed on to a set of schedulers. We have a threaded scheduler. We have a multiprocessing scheduler. Recently, we have a decent distributed scheduler, which we'll talk about in a second, too. The intermediate representation is the graph specification. And so this kind of decoupling is nice. So what is a Dask graph? So Dask graph is a dictionary of name and task, so where the value is a task. Tasks are tuples of function and then some number of arguments. It looks a lot like Lisp. Which scares some people, but it's an easy way. It's a simple specification. Arguments can be anything that's hashable. So each collection, Dask arrays, Dask data frames, has some kind of metadata that we store in each of the names. In case of an array, it's the index of which chunk it is in an array. So on the left here, we have some normal Python code. So setting a equals 1, b equals 2. We'll do some incrementing on each and then multiply the results together. And on the right, we have the corresponding Dask graph for the exact same operation. And so you can see they look fairly similar enough. It's just a slight rewriting. So Dask collections fit many problems, but they don't fit everything. Some things can't easily be encoded in an array or data frame or even the bag abstraction. And so you might want to drop into the graphs directly. Well, the good thing is that the schedulers are separated from what builds the graphs. And so you can use the schedulers and the specification directly. So here is a sample workflow. You might have a loading function, a cleaning function, something to do an analysis of all the files together, and then something that stores. And so you can see the graph on the right there as to what it actually looks like if you were to do that. And at the very bottom, we're actually creating the graph. So we're creating a couple loading functions, one for each file. We'll clean each file. We'll analyze all the files together, and then we'll store them. And so that's nice, and that's readable. But it could be a little more readable. So we have another collection that we haven't talked about yet, is Dask imperative, which uses a decorator. It's a little like joblib, if any of you have experience with that. And so you can decorate functions, or you can use that inline too. And this automatically builds up a Dask graph, which can then be run. So you decorate functions with do, and then you can use them. And there's some limits to what works, and I don't have enough time to talk about that, but it's in the docs. There's a fairly good example of this. And so we find this is a pretty good way of working with things that don't quite work with arrays or data frames. And so with that, you can create custom workflows. So some recent work has been done on using scikit-learn with Dask, specifically the grid search and the pipeline. So on the right there, these are far too small to see what's actually going on. A little complicated, is the grid search and pipeline one. And at the bottom, we have cross-correlation model. And so both of these were created just using Dask imperative and some Python code. And it's extremely readable. There's a blog up on Matthew Rocklin's blog about it. So distributed, I mentioned that earlier. It's been asked for. It's a common thing that people might want to do. Dask was started with a single machine thought. So thinking of single large workstation. And I love the title of this paper. Nobody ever got fired for using Hadoop on a cluster. This came out of Microsoft Research a little bit ago, and it's got this nice quote in it. For workloads that are processing multi-gigabytes rather than terabyte plus scale, a big memory server may well provide better performance per dollar than a cluster. And we found that using this, trying to scale up rather than scale out is a nice thing, and it works for a lot of common problems. You don't necessarily need to go distributed for a 50 gigabyte data set. You can definitely do that on a single machine. But we have been working on a distributed scheduler. It's up here. This is the documentation for it. It lives outside of Dask. There was one that was inside Dask, and that got nuked in the latest release. It's no longer there. It was a little bit buggy. This is a lot more robust. Mentioning the Blaze blog again, there's a blog post up recently using the distributed on HDFS alone with absolutely no Java. So pulling files from HDFS and computing on them in Python using no Java code at all. And that's all done with distributed. So takeaways. Python can still handle large data using blocked algorithms. You don't necessarily need to scale up to a bigger machine. You can load less in memory at a time. Dask collections form task graphs expressing these algorithms. Dask schedulers execute these graphs in parallel. And Dask graphs can be created directly for custom pipelines. You don't need to use the collections. You can create graphs externally. For further information, I got a pile of links up here. So we have our docs. We have examples up in a separate repo. Some of them are actually active with Binder, so you could just go online and try them out on Binder yourself. It's a great service. We're really enjoying using it. Blaze blog right there. We often blog about projects in the Blaze ecosystem. Dask is one of them. We have a chat up on Gitter and then GitHub for issues, or if you'd actually like to get involved, we would love to have you. Questions? I think I have a few minutes. Yes?
In your data frame example,
Mm-hmm.
did you get that parallelism because you had multiple files, or could you have had one giant file and just chopped it up?
Yes. So there's a few caveats to that, but in most cases, yes, you can get parallelism in a single file. We split, we pick a random index into that file along characters, and then we seek to the next new line, and then we break there. And so we're able to split CSV files into a couple different chunks if you have a big one.
But not logical chunks like dates?
No, not logical chunks. You would have to somehow take care of that yourself. Yes?
For the Pandas example, the data frame example, you showed that you weren't really using more than one CPU much. You also mentioned that your scheduler by default uses threads. Is there a process?
Yes. And so because the question was, can you use multiprocessing? Is there a multiprocessing scheduler? And yes, there is. You can actually drop that in. So the scheduler interface is the same across all of our schedulers. And so it's a setting. You can set it globally. You can set it locally. We have a context manager. Or you can do it computation by computation. It's a keyword to the compute method. And so that just drops in and say by default, the data frame uses threading. Array uses threading. Bag uses multiprocessing. And we find that for most things, that works out OK. And Pandas is more and more recently released in the guild. So value counts actually is an extremely fast computation. We can get pretty good parallelism on that. Yes?
For your distributed scheduler, does it handle job failure in any critical way?
Yes, recently. Just to clarify, the distributed scheduler is extremely alpha right now. So do not depend on it. But if you want to try it out, we would love comments and feedback on it.
Basic question that, the language itself is interpreted, right? How does it build the graph? It just parses the whole code, or?
Which part?
You said the Dask graph, right? How does it build it? Like it parses the entire code.
Are you talking about using the collections, or are you talking about
Dask.
So the collections build them up, and so we're working internally inside these array-like or data frame-like objects, building up a dictionary expressing the graph.
So this all happens in runtime?
Yes. Any other questions? Yep.
What are some good, mental shorthand for when this is a good tool to use? Like, when your data's too big for your memory, or when you want to get more out of your laptop, or when it's not you don't need a cluster, but it would be nice to get your big EC2 box to do more. You know what I'm saying? Like, what do you think about this?
Yes. So So personally, I really enjoy working with larger data sets on my laptop. So again, that Ocean data set was really fun to play with, and I was doing that all on my laptop, which is about 16 gigabytes of RAM. And so that 50 is a lot bigger than that. Let's see, Stefan Hoyer at Climate Core uses Dask daily as part of his library X-Ray. And so he's using that for processing up to a terabyte or two of data of a big array-like things. And he's getting good use out of that. So I'd say for arrays, we can get faster than NumPy on a large enough size. I think that probably is computer dependent what that size is. So you can actually get parallelism, and that's a good thing. But you can also get out of core. For data frames, the benefit right now is mostly just the out of coreness. You can work on larger data frame-like things that are bigger than your memory. And we're primarily targeted at the single workstation, single large machine problem, and slowly branching out into potential distributed use cases. Yep.
It's a follow-up to that question, in fact. So when you did visualize, like, graphs were generated at that time, but there's nothing done until you did a compute.
Yes.
So that gives me a sense that actually graph is more of a static rather than you are generating this graph right before you start in computing. So if anything changes between, you'll have to regenerate the whole graph all over again. Is that right?
Let's see. So if I understand your question, the graph is built up off the data. And so if your data changes, if you want to run it on a bigger array per se, you have to rebuild the graph. But the building of the graph is pretty cheap. It doesn't take much time at all. And so for problems, that's the other bit, is the scheduler has some overhead. So the scheduler has about a millisecond or so per task max overhead. And then you also have the time to build the graph and start up a thread pool or a process pool. So there is some overhead on running those things. But each task should be a lot larger than the overhead for that. And so we find that the building of the graph and the running of the scheduler is very, 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 very small compared to the actual tasks. Does that answer your question? Or?
Yeah, so,
OK. I think we're out of time now, actually. So thank you.